Hi everyone, this is Tranter. I'm a postdoc in the Electrochemical Innovation Lab at UCL, and I'm going to be talking to you about thermal battery modelling across scales. So thermal problems in batteries are inherently multiscale in their nature. The heat is produced as a consequence of ion transport and electron transport, and also entropic changes in the electrodes at the microscale level, and also at the macroscale by electron transport in the current collectors, interconnections and busbars. That heat that's produced is dissipated at the macroscale at the cell or pack boundaries, and the temperature profile that results is fed back into the electrochemical behaviour of regions of the cell. So this work demonstrates an efficient and versatile method to couple together these two processes with applications to single cells and packs, and hopefully that gives insight into the performance and improvements into cell design. The first study we did, we chose to take an 18650 cell and scan it in an X-ray CT machine to get a tomography image, and that formed the basis for the computational domain of the model. And we also did SEM and got more detailed images of the electrodes to get things like particle sizes and porosities, which are variables in the model. So the computational domain is extracted directly from the CT scan, and the current collectors that form the spiral around the jelly roll are identified, and created from that is a resistor network that determines the global current transport. The sections of electrode in between the current collectors are modelled like individual battery units that are connected in parallel, and this leads to a 1+1D description of the cell, where you have the electrochemical models running orthogonally to the current collectors. The resistor network in the current collectors determines the global current and heat transport, and the heat is generated by the electrochemical processes that go on and the ohmic processes that go on in the current collectors. This heat in individual layers is transported across layers, and that affects the temperature-dependent variables in the electrochemistry, so it's this coupled system that works together. Heat is removed at the outer layer of the cell, and the inner layers are thermally insulated. With this framework that we're developing, we can actually look at degradation. So jelly rolls actually tend to deform over time and they delaminate, and our framework should be able to capture this very accurately in the future. And we could also flexibly specify the number of tabs by picking nodes for boundary conditions. And we can also control the heating on a nodal level as well and specify uneven cooling, which I have some results to show you of later. So the governing equations are those defined by the Doyle-Fuller-Newman model, which has been implemented in PyBAM, which is an open source Python package that's been developed across multiple institutions as part of the Multiscale modeling project that I'm part of. We have governing equations for charge conservation, current, mass transport, diffusion in solid particles. The reactions are determined by the Butler-Volmer equation, and there's an energy balance to determine heat transport, with the heat source terms primarily being from the entropic changes and then Joule heating. The first results I'm showing here are the snapshots of current density at different states of charge. On the left, there is a single tab for each electrode, and on the right, there are 5 tabs for each electrode, spaced evenly throughout the layers. So the heterogeneity in current density is much greater for the single tabs, where the current has a further distance to travel between being collected and being distributed. And this heterogeneity arises because there's actually a reasonable amount of resistance in the current collectors. The length of the jelly roll is quite long. For an 18650, it would range from about 60 centimeters to a meter, and for larger cell formats such as 21700, you're looking at more like 1.5 to 2 meters, depending on the thickness of the layers. And because they're only 20 or 30 microns thick, you actually get a reasonable resistance in them. And so imbalances in the current can also lead to imbalances in the thermal behavior as well. And this will have a knock-on effect on cell performance and degradation mechanisms. So we can also look at the effect of changing the cooled surface area and different heat transfer coefficients at the cell boundaries. And if you have a battery pack that is being cooled with a water jacket, that water jacket would tend to snake in between the lines of cells that are in your module. So you actually only about a third of the surface may be getting the cooling, and you may experience quite severe internal temperature gradients as the model predicts. So we have a couple of different cases here. The 28 watts per meter squared per Kelvin heat transfer coefficient corresponds to basically a cell sitting in ambient air inside an atmospheric chamber with a slight convection cooling effect, and the larger 100 watts per meter squared is more forced cooling region. But with the cooled surface areas, you actually have a comparable total heat loss between two of the cases, the red and blue case, and a comparable average temperature. But you can see with the uneven cooling the difference. So the envelope of temperatures there shown in subplot D is around 5 degrees for the more severe cooled case. And that there have been other studies that have shown that only a couple of degrees will actually make a big difference in terms of where lithium tends to plate, and so that will be a future study for us. Scaling up the model is also very easy, so we can determine parametrically as well as from images the number of layers in the model. And I used the same cell parameters that were actually gathered by our colleagues in Birmingham and Warwick for an M50 cell, and I applied it to the new Tesla 4680 cylindrical cell format. And Tesla have actually made another innovation, which is to design tabless current collectors. So they're actually using the edge of the current collectors themselves as tabs effectively. And so on the top left, you can see where you have the traditional tab design, one on the inside, one on the outside. I'm only showing 5 layers just for clarity, but there is actually 40 layers in the model. And then on the bottom left, you have more or less tabs everywhere. So this has a big effect on both the current density heterogeneity and also the total heat produced. So in the middle there, you have A, C, and E being the traditional tabs, and B, D, and F being the Tesla tabs. And the total heat produced is largely dominated by this ohmic loss in the current collectors, as you can see there in subplot E. You have around 8 watts associated with ohmic loss in the current collector, and that has a big knock-on effect on the overall temperature. So it's reaching an 80 degree temperature difference above ambient there, whereas with the Tesla tabs you have that ohmic loss in the current collectors is more or less non-existent, and you only have maybe a 25 degree increase over ambient there, and that's just for a 1C. So because these cells are larger, they have a much higher capacity, and 1C equates to about 18 amps. And over on the right there, we see a similar shot to the one I showed before for the 18650. You have these regions where at different times, different regions are experiencing a higher local current density. And that plays into degradation mechanisms as well. And these kind of wave-like regions, the wave-like behavior of kind of switching on and off different regions for high current and low current occurs because of local changes in local resistance. So we've taken the framework to another scale again, and because in the single cell model we have neighboring sections essentially acting like individual batteries in parallel, we can actually measure batteries in parallel in a pack. So we have a study here that's been conducted mainly in the lab with some model backing, and we have parallel strings of 8 cells. And changing the terminal locations to be common end and opposite end, we see differences in the variation that each cell experiences over its discharge, and also correspondingly differences in temperature. So our models are predicting this, and we can see that would have an effect on degradation as well. Taking this step further, we built a module, and this was in collaboration with D2H Aero, and we were funded with an Innovate UK grant to do this work, but it's come as a direct result of the work being undertaken in MSM. So we together built a CFD model to analyze the airflow in and around the cells and calculate heat transfer coefficients very accurately for individual cells, and then taking the PyBand model and actually making it into more of a black box, I was able to implement a Simulink electrochemical model where I can accurately determine the connection resistances and the busbar resistances. And so the rig is fully censored. It has 32 21700s in a 16P2S configuration, and the cell temperatures that we're measuring in the rig align very well with the model predictions as well. So there's good promise here to take that forward. And here are some references. I'd like to thank all my collaborators in UCL and across all the MSM institutions and the PyBand team. So thanks for your attention.